Hey everybody. So I hope that you did well on the test. I'll be grading those and getting those back out to you. Today we're going to kind of start something really fun, something really awesome. We're going to start networks. Network optimization is a subcategory. It fits into linear programming, but if you were to go get a graduate degree focused on optimization, you would learn about networks in your first LP class, but then you'd probably also specialize more in a networks class where you dive really deep, because there's a whole lot of really neat network optimization problems to research. You have things like longest path, shortest path, minimum cost, things where you try to break networks, strongest networks. Just so many assignment problems fit under these, which are also really neat problems. So a lot of awesome applications come from networks. So that's where we're starting, is the just basics, minimum cost or minimum flow networks. Okay, so now, why does this fit in the subcategory of linear programming? Every single network can really pretty simply be modeled as an LP. There's no need to really learn anything else if you could do that, but I'll tell you why we learned this thing called the network simplex. Just something a little bit different. Alright. This handout will be posted in the email with the video. Now each network is going to be a graph. If you've never studied any graph theory, that's okay. You don't need any real deep graph theory. You just need to know some terminology. There'll be nodes, or little dots, vertices, and those will be connected with edges or arcs, or whichever terminology you want to use. Okay, and I'll draw you an example in a second. Each arc, because the way these networks are going to set up is each arc will have a cost associated with it, and each node will have a supply and a demand. And you'll see when I draw the first example how that will work out. Okay, now we can model these as a linear programming problem. Each arc will be represented by a variable xij. Okay, xij will be the arc that goes from node I to node j. Okay, so for example, x to 5 is the arc that connects 2 to 5. Okay, really simple. Now, so each arc is represented by a variable. That means each node must be represented by a constraint, and that's true. These are really special constraints. They're called flow conservation constraints, or the mathematician that kind of coined the phrase is Kirchhoff. Okay, I think he's Eastern European or something like that. You could Google Kirchhoff just to see. Alright, now we've actually seen some flow conservation constraints, or I just call them conservation constraints, when we did the problems that had you storing material over till the next quarter, the quarter planning periods, production planning, multi-period production planning problems. So this is kind of similar to those. Okay, so let me give you an example, and then we'll write it as an LP just so you can see all those things that I just mentioned. Okay, so our first example is going to just be a very simple network. I'll draw it in black first. It'll look something like this. So I'll have a very simple network. Let's just do 4 nodes. Node 1, node 2, 3, and 4. Okay, and we're not going to have arcs everywhere, but our node 1 is connected to 2 and 3. 2 can send stuff to 3. 2 can also send stuff to 4. And let's say that 4 can send stuff to 3. Just very simple arcs here. Sometimes you have arcs go back in each direction, or so there's how our network's going to look created. That's nodes and arcs. So pretty cool. Now each arc is going to have a cost associated with it, a unit cost. So however much I push on this node will cost me 4 per unit. So these are going to be the cost. And I try to come up with ways to make sure I don't get all my numbers confused. So sometimes I put this was something I came up with myself. I put little triangles around my cost. It just made them stand out. Of course, I have colors here, but you may not be taking notes in colors. So let me give you all the cost, unit cost for using each arc. So every time you push something here, it's going to cost you 1 per unit. 2 that way. 1 to 3 has a cost of 3. And 4 to 3, let's say it has a cost of 5. Okay, so each arc has a cost for shipping material over this part of the network. Now each node is going to have a supply or a demand. So node 1, for instance, has a supply of 7. And like I said, I came up with my own little, I like to put boxes around them. You don't have to. A lot of people just write the numbers and try to remember what they mean. Let's say node 2 has a supply of 5. Oh, that's kind of a sloppy 5. Rewrite it a little prettier. A supply of 5. Node 3 has a demand of 9. So the demands, the way to tell the demands and supplies apart are just whether they're positive or negative. Okay, so this node 1 has a positive 7, so it has 7 units of whatever we're shipping. And node 3 here has a negative 9, so that means it needs 9 of something. Okay, and let's see, this one has a demand of 3. Okay, so there's our first network. Okay, we're not going to do anything with it yet, besides model it as a linear programming problem. Okay, and so these are really super applicable in real life network problems. I love them. I love math that has real life meaning to it, because you could think of the cost as a distance, you know, and say these are stops with factories shipping stuff, and they have to ship so many or this could be hospital systems, and you know, this hospital right now with everything that's going on, so they need 9 ventilators, and these need 3 units of ventilators, and these people have extras, and so they're going to ship them, and so we want to try to send them as fast as possible, so the shortest distance, you know, the least amount of cost, or something like that. These have a lot of real application to them. They're really neat. Okay, so I just love math that has application. So this can be modeled as a linear programming problem. Okay, so here's how the LP is going to look. Let's see if I can fit them both in the screen at the same time. There. So remember so follow my mouse here. Keep your eyes on my mouse. Each arc is going to be represented by a variable. So the arc going from 1 to 2, x12, is this variable right here. Okay, and we know the cost on it. The cost is 4. Well, that's really easy to write then, right? So each arc gets a variable. So the arc going from 1 to 3 is x13. And what's the cost on it? 3. So you can see writing this, x23 will have a cost of 2. x43, that's down here, have a cost of 5. x24 will have a cost of 1. So writing the cost is really easy. Okay, now we get to writing the constraints. Okay, so in the constraints here, what's going to happen is everywhere there is a tail where stuff is leaving, you can also switch the convention here if you do it consistently throughout. You have to be careful with signs, but this is the way that's commonly used in most textbooks. Everywhere that an arc is leaving a node, they call that the tail of the node, gets a positive 1. So 7 is shipping away from here and away from here. Okay, so node 1 is going to have this first constraint right here. How much supply is at node 1? 7. How much should we be shipping away from node 1? 7. So these two need to equal 7 to ship the node away. The reason is this is called a balanced network, because notice the supply and the demand are equal. How much supply is there here? 12. How much demand is there here? 12. So these conservation constraints are should all be locked in even. Okay, equal. So everywhere there's a tail gets a positive 1 in the coefficient. Everywhere there's a head gets a negative 1 for a coefficient. Okay. So the second node, it has 1, 2 coming into it, so there's a head. So it should have a negative 1x12, and it should have a positive x23 and x24. x23 and x24. And it should equal 5. So whatever's coming in, you know, that gives it more supplies than 5. Say we shipped all 7 here, it would have 12, and it would need to ship the 12 to these two. Okay. And so we just fill this out looking at each node. Alright. And hopefully there's no questions. And of course, still keeping non-negativity. We want all of these flows to be positive. I don't want to push any backwards and violate how we've set up this thing. Now I want to point out some really interesting things. Well, one really interesting thing that'll be really powerful. Look at each column. Okay, ignoring the cost for a second, each column has 2 entries in it. Do you see that? That's really powerful. Notice each entry is a positive 1 and a negative 1. Positive 1, negative 1, positive 1, negative 1, positive 1, negative 1, positive 1, negative 1. That's really neat. We'll come back to that and use that later as something really powerful. Okay? That should make sense to you, though, because remember, each variable represents an arc, right? And each column is just a variable. This column is for the variable x1, 2. And each arc is starting somewhere and ending somewhere. So a positive 1 and a negative 1. Start somewhere, end somewhere. Positive 1, negative 1. This arc does not touch any other nodes, so it should not have any other entries relating to the other nodes. So each column relates to one variable, and every one variable represents an arc. And every one arc is going to have one tail and one head. So every column will have a positive 1 and a negative 1 in it. That'll be really important in a little bit, okay? So now let's scooch on to the next page. All right, so networks are pretty awesome, and they provide an advantage because we can actually solve this on the network instead of writing and solving the linear programming problem. So yes, I showed you that it could be written as a linear programming problem. You could solve that one as a linear programming problem, but we usually don't want to. The reason being that LPs with networks tend to have a huge amount of degeneracy in them, and so you get cycling issues. This is the same thing as the airline scheduling problems. Those are assignment problems, which are a type of network problem, and they have bunches of degeneracy and cycling. I told you they would take days of computer code running to solve. So typically with those, they use dual methods to terminate early and get upper and lower bounds. But if it were a small enough network that they could actually draw the network and solve over it, they would do that instead of solving the LP. Okay, so what we're going to do is solve on the network, on the visual graph that we drew. We'll solve on this thing. So that's pretty interesting. Each new pivot, instead of drawing a new matrix, we'll just draw a new network. Okay, so we're going to start learning the network simplex. So we got to lay some things out, though. This is going to work exactly like the normal simplex algorithm. So that means we need something to be extreme points. We need some way of finding the most attractive way to cycle some variable in and cycle one out. We need a way to do a pivot. We need those things, and we should be able to come up with a network, a simplex method for these networks, okay? So first things first, we need basic feasible solutions, right? That's how an LP works. Doesn't it just visit one extreme point to the next, one BFS to the next? So I'm going to go ahead and just not make you struggle too long. Go ahead and spoil it for you. Basic solutions, when we're talking about graphs, are rooted spanning trees. Okay? Rooted spanning trees. Let me tell you what some of these are. Rooted is something we'll kind of fuzz over at first. Rooted just means that it has a root. We just need a root. I'll tell you about that later. Don't stress over that. What spanning means is that it spans all the nodes. Okay? Spans all nodes. So whatever we have, we can't have like 1, 2, 3, and then 4 not being connected to anything. Okay? It's got to span all the nodes. All of them have to be connected to be a rooted spanning tree. Okay? And a tree means that it's a connected graph with no cycles. So connected and no cycles. Okay? What the difference in spans and connected is, if I did this, all these are all the nodes are connected to something, but are spanned, but they're not connected. So we need to make sure they're all touching. Now we're not allowed to have any cycles. Something like this makes a loop. So I'm not allowed to have that. So no cycles, okay? Those are the important part. So no cycles. We got to touch every node and they got to all be connected. Okay? Hope that makes sense to everybody. Now this is a basic solution. We need a basic feasible solution. That just means we're going to want it to be a feasible rooted spanning tree. And feasible just means that all of our supplies and demands are met appropriately. That's the feasible part we're talking about. If I only have 3 things at node 1, I can't ship 5 from it. That would be infeasible. So it's pretty easy to keep up with feasibility, okay? Alright, so there's a basic feasible solution. So what that will look like when we're back over here on a network will be I'll have the nodes 1, 2, 3, 4, and they will be connected and spanned with no cycles, and that will be one of the basic feasible solutions. We got to keep up with the flows. So I always keep the original here, and then I'll put, instead of the cost, whenever we're doing pivots, I need to know how much is flowing on each arc. So you'll see when we do an example, okay? Now, so we have BFSs. How do we pivot though, okay? How do we choose what's most attractive? How do we do all these things? And so that's a good question. So I'm going to take the long way around to answer this one. So remember whenever we learned about duals, just last few lessons, I told you, look, we had primal feasibility and dual feasibility. Those were powerful things, but we also had complementary slackness. That's an extremely powerful idea. If you don't remember that, go back and watch the videos from the last few lessons. Those 3 pieces make up the KKT conditions, which means you have an optimal if they're being met. Okay, necessary and sufficient. If you don't know what that means, don't worry about it. Okay. Now think back to the columns. Each column in our linear programming problem has a positive 1 and a negative 1. So imagine that you're going to write the dual. Okay. We can exploit this special structure. So a dual, let me go back to the LP and let's think about it. Remember, a dual would just basically turn this thing on its side, right? So each dual constraint would have a positive 1, a negative 1, and it would be less than or greater than or equal to the cost for that same variable, right? Because these would be the right-hand sides. Each dual constraint would be a positive 1 and a negative 1, and related to the cost. Okay, now back to where we were. We're going to be able to easily see that each dual constraint will look like this. One variable minus another one is less than or equal to the cost on that variable. Okay, but let's rearrange this. Let's add and subtract the y's over to the same side as the c. Okay, and this is what we'll get right here. This is a very, 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 very powerful thing that we're going to use. This will keep us dual feasible. So if we could stay primal feasible, that will be easy. Just keeping the flows working right. Dual feasibility, we'll check it with this thing right here. And that actually will play into what's most attractive, if we have anything attractive, and how we pivot. It'll all be done with the duals. This is almost like the dual simplex, where we're primal feasible because that's just how we're going to keep it. And then we're going to adjust the duals and do pivots until we're dual feasible. Okay, now the powerful last piece of this is complementary slackness. Okay, so stay with me for a second. Complementary slackness says the x variable times this dual constraint. Well, we know they're equal signs, so the slack on this is either 0 or not 0, right? But if this is 0, we don't care what this is. We already know it's got to be greater than or equal to 0. If this is not 0, okay, that means all of these things must equal 0. The cost minus the y1i plus the yj. Okay, so that's actually what we're going to be doing. So this seems like a lot, but once again, all we're going to focus on is the same thing, the cost minus yi plus yj. The same thing here, cost minus yi, y minus yj. So that's the one part we want to keep buckled in, and that's mainly most of the math we're going to be doing is focused in on that part. That's the most important part. Okay. Alright. So I got my notes here trying to keep up with where we are. So just another way of writing this is that's the original cost. Let me try to just get some space to write here. This is the original cost. Cost. Now these are dual variables. So this is minus the dual at the tail and plus the dual at the head, at the arrow. Okay, so that's all we really want to stress over trying to keep up with is the original cost minus the dual at the tail plus the dual at the head. Okay, so we're going to need to come up with these dual variables and hang on to them. Okay, so now none of this should really make sense to you yet until we do an example. We'll be looking at original cost minus dual plus dual minus the head plus the tail over and over and over again to do every single pivot. Okay, so let's do an example, and that'll be where we'll end today. We're going to do a simplex, network simplex. Are you excited? So I'm going to suggest while we do this that whatever you're copying down, you keep the original table easily in view. Okay, and let's see, this example is going to be a little bit bigger than the one I drew earlier. It's going to have 5 nodes. Okay. Make sure I get all my arrows going the right direction. Okay, let's see. Have both of these feeding into 3. 3 go into 4. And 4 sending some to 5. Alright, let me put the cost in red. Because of space, I probably won't try to draw my triangles. Let's see, the cost for this one is 5. Over here is 6. I will label 1 so you know that the red things are cost. Let's see, what's the cost on this one? Actually, one that we gain on if we use -4, -2, 2, 4, 0, a freebie, and 3. And this happens in real life. You have negative costs sometimes because you have certain perks with certain companies and things that using certain avenues they may give you more than you actually take away or than it actually costs you. Alright, let's see. So the supplies and demands, we're going to have 2 at node 1, 5 at node 2. At 3 we're going to have 1. Okay. At node 5 we'll have a demand of 4, so -4, and here we'll have a demand of 4. So let's double check to see that it is a balanced network. My supplies are 2, 5, and 1, that is 8. My demands are 4 and 4, so that is balanced. So these are supplies and demands. Okay. Alright, so let's keep this visible. Okay, I may not be able to keep it on my screen, but keep it visible for you, okay? So here's what we need. We need a root. All that is a little arrow sticking off, okay? And we need a starting solution. For now, I will give you a starting solution. Okay? Depending on how deeply we go, it may depend on whether I teach you how to get a starting solution or not. So I will give you a starting solution, just like we had with a lot of the LPs. But know that it doesn't magically appear. There's actually some work involved to get a starting solution. Okay, so let me draw our starting solution. Okay, and so this is what we're talking about with a rooted spanning tree. Just have a root sticking off there, something pointing to nothing. Let's see, so our first rooted spanning tree goes 1 to 5, 4 to 5, 3 to 4, and 2 to 3. Okay, and so here's what we're going to do. These over here are the cost. That's why we keep this one kind of separate. This is the original one, This is good to know. What we're going to do here is tell you how much is flowing on each of these. So these are different than the cost. These are the flows that I'm going to write beside each arc. So for instance, 1 is shipping to 5. Well, how much did 1 have? It had 2. And for this thing to be balanced and to send or receive all it had or demanded, this has got to ship 2. So it shipped 2 to node 5. Okay? Do you understand that? Now, what was the demand on 5? What was 4? So if it's getting 2 here, it needs to be getting 2 here to be balanced, right? To be getting 4. Its demand was 4, so it needs to be getting 4. Okay? Awesome. How much did 2 have? Let's go to this end. 2 had a supply of 5, so how much is it shipping to 3? It is shipping all 5 of what it had. Okay? So it ships 5 into 3. How much does 3 have? 3 had 1, but it just got shipped 5, so how much does he have? He has 6 now, and he's sending all 6 over to 4. Well, let's make sure 4 gets its demand met. Node 4 had a demand of 4. It gets 6 and sends 2 away. Does it have 4? Yeah. So that's the primal feasible part. And because we're always going to make sure the flows are sending and receiving all the demands and supplies, we'll always keep primal feasibility. So are there any questions on that? Take a second to look and stare and soak it in. Okay. So let me label these. These in purple are the flows. That's what we call it. It's how much flowing on that arc. All right, now, how we do this is we need to keep up with the dual variables. Okay, and there's going to be a dual variable associated with each node. Ask yourself why that makes sense. In the primal LP, each node was a constraint. That means in the dual LP, each node will be a variable. Okay, so here's how we're going to do this. We're going to start at 1 and just give it a dual of 0. So there, your dual is 0. Okay. Start where the root is and go ahead and say that has a dual of 0. That's why we have this little root. See if I could label that as well. This is the root. It's the starting point. So we give it a dual of 0. Okay. It doesn't actually matter what you start at, but it makes it confusing if you don't start at 0. So, okay, so then let's trace this thing here, okay? Now remember, complementary slackness tells us, let me write it, the x variable is going to be equal to the original, not equal to, but multiplied by the original cost minus the dual tail plus the dual head, and complementary slackness says these two things multiplied together must give you 0, right? Well, x has a value of 2 right now, not 0. So what's the only way that this is going to be 0 is if this is 0. So this is why we want to keep the original table, not table, but the original network over here, so that we have the original cost. So what is the original cost going from 1 to 5? It is 2. So the original cost is 2 minus the tail plus the head has got to be 0. So we should have one of these values. We have right here, that is the tail of this arrow shooting away, right? So what is the dual value of the tail? It is 0. So all we're going to do is fill in the blank to get the dual value on this node. And we work our way around the whole tree until we have all the dual variables written in. So to equal 0, what must we be adding to 2? It's got to be -2. So what's the dual variable here? -2. Okay? So now I'm going to do this all the way around the tree. So 5 to 4. So what was the original cost? 3. Minus the tail plus the head. It's got to equal 0. So let's see. I don't have the tail this time because the tail's at 4. I have the head. That's -2. Right? So bear with me here. 3 plus a negative 2. What does this need to be to make it equal to 0? This needs to be a 1, because 3 minus 1 is 2, plus negative 2 is 0. So this one is 1. Awesome. So let's keep going here. What's the cost on 3, 4? 0. Minus the tail. Minus the tail plus the head is got to equal 0. Let's see. What do I have this time? I have the head this time. It's a 1, right? So what's the tail got to be? It's got to be 1. Negative or minus 1 plus 1, 0. So this one's a 1. And finally, the last one. What's the cost from 2 to 3? 4. Oh, negative 4. So negative 4 minus the tail plus the head has got to equal 0. So negative 4. I don't have the tail. I have the head as 1. So let's see. Negative 4 minus negative 3. Minus negative 3 would be negative 1. Plus, yeah, so that's it. Negative 3. Whew. Awesome. Okay, so we filled out all the duals. Are there any questions on me doing all this work to fill out all the duals? Okay. Now, so once we have the duals, the reason that we find the duals is that these dual variables are how we're going to find the reduced cost. Okay? How we're going to see what's most attractive. So now what we have to do is check this for every variable that's not in the basis, every arc that's not in the basis. I do want to point something out. This is almost like the dual simplex, because notice the duals, I have a negative 3 and a negative 2. They're not all feasible. So we're going to go and push until we're feasible, and hopefully we'll be optimal then. Okay, so let's see. Let's run down all the possible x values. Which ones do I not have? I don't have x12. We got to check to see if that's attractive. I don't have x13. Got to check to see if that's attractive. What am I missing? x23? No, x23 is in there. x42. x45. And I think there's one more. Let's scroll down a little. Well, I could probably fit it around here. x53. Are those all the arcs that are not in there? 1, 3, 1, 2, 1, 4 is in. Or sorry, 2, 3 is in. 3, 4 is in. 4, 2, 4, 5, and 5, 3. Okay, awesome. So what we're going to do is we're going to do the same formula. The cost. We're going to do the cost minus the tail plus the head. And we got the dual variables this time. Okay, so for x12, the cost is 5, right? What's the cost on x13? 13, it was negative 2. Minus plus x42, the cost was 6. 6 minus plus 45, the cost was 3. Minus something plus something. And 5, 3, the cost was 4. Okay? Minus the tail plus the head. Okay, now we got to find the tail and the head dual for these. So from 1 to 2. 1 to 2. No, 1 to 2. So what is the tail value? It's 0. What's the head value? It's negative 3. So let's see what we have here. 5 minus 3 is 2. So that's actually its reduced cost. All right, let's look at negative 2. So 1 to 3. 0 and 1. Tail to head. So we're considering if this arc right here is attractive. So what is that? That is negative 1. Okay. 4 to 2. So we got the cost. The duals 4 to 2 are 1 and negative 3. 1 and negative 3. Let's see what that gives me. That gives me reduced cost of 2. Let's check 4, 5 here. Right, 4, 5. Trying to make sure I didn't miss any. Oh, why am I checking 4, 5? 4, 5's in there. Watch, if you check 4, 5, look what you'll get. A dual of 1. The tail is 1. The other piece is 2. That's 0 because that one's a basic variable. I don't need to check that one. My bad. I got excited trying to look at both graphs. So x53. So what's the tail is negative 2. What's the head? It's 1. Let's see, 4 minus a negative 2. That's 6 plus 1, 7. These are the reduced cost. Okay? These reduced cost work exactly like your normal reduced cost are. Y'all see these? These are the reduced cost. Are any of them attractive? Yeah, this one is attractive right here. Attractive. Okay? So what's going to enter? X 1, 3 will enter. Well, then how do I tell what leaves? Well, let's see. X 1, 3, let's draw it as a dotted line, since that's what's going to enter. It's going to enter. Okay? Now, look, it makes a cycle. Does everybody see the cycle? Okay? So what's going to happen here is this should push one of the arcs out. Okay? So in this cycle, because I'm not allowed to have a cycle, either this arc, or this arc have got to leave. 2, 3 doesn't have part of the cycle, so it's got to stay in. So one of these have got to leave. So we start pushing flow through, and we see which one of these gets pushed down to 0 first. Well, this one's at 6. We're pushing in the same direction. It's going to just increase, not push down to 0. This one's also pushing in the same direction. So we always move in the direction of this entering arc. The only one that's going to get pushed down to 0 will be this arc right here. So which arc leaves? 1, 5. So X 1, 5 leaves. Okay? So are there any questions on that part so far? And so all we do is the same exact thing all over again. Okay? So we draw this new network, this new rooted spanning tree, and we can check what the cost is and what we're going to be at as far as, let me get all this out of the way, group this and move it. So let's shrink it and move it. I'll move it over here. So let me draw this new network now, okay? So 1, 2, 3, 5, and 4. Okay, so we have, this is still our root. 1 to 3 is now in there, and everything else that did not leave is still in there. We got to refigure what the flows are. Okay, now 1, 5 is gone, so there's our new rooted spanning tree. So let's see, what are the flows? Well, this one had a supply of 2, and that's the only shipments it's making, so it's sending all 2 of them that way. This one had a supply of 5, so it's going to send all 5 that way. So now 3 has 2 plus 5 plus his 1 that he had. So he's sending all 7, not all 7, all 8. If I could add, it'd be good. All 8 over to node 4. Now node 4 had a demand of 4, so he has 4 extras that he's going to send on to node 5. And 5 had a demand of 4, so everybody's supplies and demands are met. So we are primal feasible. So now we have to adjust the duals again. Okay, we're going to still say the rooted one is 0, and we're going to do the same thing. Cost minus the tail plus the head has got to be 0 for all these. Okay, so let's see. What's the cost on 1, 3? It's negative 2. So I need some space to work. So let me just move that out of the way. Get you out of the way, because I need to see my cost. So we're going to go cost minus the tail plus the head. Let me make this look like, I don't know why I wrote plus the head. Okay, it's got to equal 0. So what's the cost there? Negative 2 minus the tail is 0 plus the head. Whoops. It's got to be 0. So what does the head have to be? It has to be 2, right? So the dual on node 3 has got to be 2. Okay? So now, let's connect node 2 to node 3. What's the cost from 2 to 3? Negative 4. Minus the tail plus the head. It's got to equal 0. I don't know the tail, but I know the head is 2. So negative 4 plus 2 is negative 2. So this should be minus negative 2. right? Minus -2. And that will make it equal to 0, right? Alright, let's keep searching here. 3 to 4, what's the cost? 0. Minus the tail plus the head. The tail is 2. So what's the head got to be? So -2 plus 2 equals 0. So this has got to be 2. Okay. And finally, we get down to the last one, 4, 5. So what is the cost on 4, 5? 3. Minus the tail plus the head. It's got to equal 0. I know the tail is 2, so what does the head have to be? -1. -1. Okay, awesome. I have the duals in place. So now I can see what is attractive, if anything is attractive, and then if nothing's attractive, we're optimal. So remember, we check it the same way with the duals. Cost minus the tail plus the head. Okay. So now, which pieces are there possible? There's 1, 2, 1, 5, 4, 2, and 5, 3. So there's only 4 to check. So let's write them down. X, 1, 2, X, 1, 5, X, 4, 2, and X, 5, 3. See, I'm getting better. This time I didn't do one we already have in the basis. So what's the cost on 1, 2? 1, 2 is 5. Minus the tail plus the head is 3. Positive, so not attractive. What's the cost on 1, 5? It's 2. Minus the head plus the tail, that is 1. So it's positive, it's not attractive. 4, 2. 4, 2. What's the cost of 4, 2? 6. Minus the tail plus the head is 2. Still positive though, so not attractive. And finally 5, 3. What's the cost on 5, 3? It's 4. Minus the tail plus the head, that is going to be 7. So notice, none of our reduced costs are attractive. None of these are attractive. And so we're optimal. Now, what is the optimal z-value? How can I find that? Well, it's at these flows. I happen to know the cost on each of these, right? What's the cost on the 1 to 3? It's -2. -2 times 2 is -4. Plus, I have a flow from 2 to 3. That's 5. 2 to 3 is -4. -4 times 5 is -20. That's awesome. Plus, 3 to 4 is 8. 8 times 0, that's 0. Plus, 4 times 3 is 12, right? 12. That's all the flows times all their cost. And that will give me -12. So we're at a cost of -12. We're optimal, and these are the optimal flows. And so that's how you do the network simplex. You keep going until you get no attractives, and you keep updating the duals. Always start with 0 from the tail. Technically, I guess I spoke wrong when I said you were worried about these being infeasible. We're not worried about those because you chose the dual of 0. You could pick any value. I could pick 12, and these would all be moved by 12, and it would be feasible. Sorry. Didn't mean to mess you up in your thinking. I was thinking about something else. But anyways, pretty cool. I'll leave you with that. Y'all have a wonderful day. I'll talk to y'all Wednesday.